So let us not keep you waiting any longer. Let's welcome to the stage Nicola Fox, Director of NASA's Heliophysics Science Division.
Our ability to make dramatic progress is often only limited by our ability to access the right technology and the right information. We find ourselves at a crossroads in science. On one hand, we operate in the same paradigm that has guided the field over the past decades, ruled by data, theory, and simulations. On the other hand, we're beginning to recognize that powerful new opportunities for scientific discovery are possible through our increased data volume and sophisticated methods to explore these data. The emergence of the hyper-connected digital society and massive quantities of data that it generates has led to new analysis capabilities that literally scale to the vastness of our solar system. NASA's mission is to expand human knowledge about the universe, the solar system, and the planet Earth. In this presentation, I want to tell you some of the ways that we are accelerating our scientific discovery by marrying the wealth of data and modeling techniques to the cutting-edge technology provided by Amazon Web Services. But first, I want to tell you about heliophysics. Heliophysics is basically the study of the sun. And why do we study the sun? Well, fundamentally, we are curious people. From the very first time that people looked up at that bright light in the sky and wondered what it was, we've studied the sun. Humankind has literally studied the sun for millennia. Ancient Babylonians recorded eclipses on stone tablets. Renaissance scientists peered through their telescopes, tracking sunspots. Eventually, we took to space, and the first satellites captured solar particles streaming past Earth. Each generation has always run against the limits of their tools. And so what do? We build new ones. And so today, that allows us to have a bounty of new research questions that we need to build yet more tools to answer. But the sun is also a star. But it's a star that we can go up and visit and study up close and personal. So what we learn about our star is directly transferable to other stars in other stellar systems in other galaxies. And that will help us as we continue our search for life elsewhere. But most importantly to us here on Earth, the sun can send billions of tons of solar material hurtling towards our planet at millions of miles an hour. We call those events solar storms, and they can be very, very destructive when they get here to Earth. Fortunately for us, our Earth is protected by a magnetic field, and that blocks all of the harmful radiation from the sun. It also protects our atmosphere from this stream of charged particles that is released by the sun's magnetic field. But the sun actually does more than that, more than just impact the Earth. If I take you over the poles of the sun now, so you're looking down, you can see a sort of spiral pattern of particles continually emanating from the sun. We call that stream the solar wind. And not only does the solar wind actually impact us here at Earth, but it in fact carves out a protective bubble for the whole solar system as we orbit through the Milky Way. So it essentially inflates a cavity that protects our solar system from the vagaries of interstellar space. Now, NASA's Heliophysics Division studies everything from the core of the sun to that tenuous boundary with interstellar space, and even actually beyond. But what I want to talk to you about today is what happens when an event, a big solar event, arrives at Earth. As I already noted, the planet's magnetic field is protecting us from the very worst impacts. You can see here how the magnetic field lines on the sunward side of our planet become interconnected with those of the solar wind. And that allows a lot of energy and plasma to enter into our magnetosphere, or our magnetic environment. In turn, our atmosphere can also get very superheated, particularly the oxygen ions there. And that actually causes the whole atmosphere to expand, and that can prove problems for spacecraft that suddenly find themselves in a different environment. Also, energetic electrons flow down those magnetic field lines, hit the gases in our atmosphere, causing them to glow and form the very beautiful aurora. Now, space weather is important, and we talk about it a lot today, but even though I said that we've studied the sun for millennia, we actually didn't realize this kind of profound link between the sun and the earth until 1859. And here you see Richard Carrington, a very famous astronomer who was looking through his brass telescopes and sketching sunspots as he did every day. And he noticed while he was looking at this particular sunspot group that there were sort of bright white flashes of light that appeared, and then they kind of disappeared. He knew something had happened, but didn't really know what it was going to do. Just hours after he saw this, compass needles at the Earth began to spin. The aurora was seen at much lower latitudes than they'd ever been recorded before. And in fact, the whole telegraph system in the US was taken down for a number of days, about 4 days. Now, that doesn't sound very important, particularly if I talk to kids and I say the telegraph system goes down for 4 days, and they go, And then I say, yes, but imagine if you lost the internet for 4 days, and panic will ensue in a classroom. So if we compare it with today, so I'm showing you data here this is actually from an event in 1989. The aurora overhead is like a current system in the sky, and that current system can interfere with our power grids. This one caused widespread power outages in the northern US and Canada. This is a very important event for us because it actually demonstrated how vulnerable our power grid can be. We know that there are much bigger events in our historical record. And as we sort of put more and more technology up, mega constellations now in space, a huge reliance on power grids, we really feel that reducing our vulnerability is a national priority. Now, these big events, fortunately, don't happen that often, but what I'm showing you here is one that happened in July of 2012. It was actually the most intense solar storm event, in the 150 years since the Carrington event. And you're probably wondering why you didn't hear about it. Well, the one thing that was lucky for us was it went off the side of the sun. But had this event happened 1 week earlier, it would have been on a direct collision course with us here at Earth. And the estimates are that it would have caused about $2 trillion of damage to the US alone. So we really want to take these things seriously, and we really want to know, how to study these. And so starting in the mid-1990s and onwards, we've really focused on taking the data that will allow us to make these sort of transformational improvements in our ability to predict when one of these events is going to come. So we have our spacecraft there looking at the sun all the way through the space environment and then into all the different layers of the Earth's atmosphere. And we know that within this huge volume of data, there has to lie the clues that will tell us which of these solar storms will in fact become one of these giant superstorm, very destructive events. But it's very hard for us to look at all of these different data and find these sort of often quite hidden signatures. And even though there are dozens of spacecraft collecting data, the data is still very sparse. Distances covered by a solar storm are vast. I mean, they're 93 million miles from the sun to the Earth. On top of that, disturbances that leave the sun can change during their transit to Earth. So, something that looks quite benign on the sun can then be very destructive when it reaches the Earth. So just like major storms that you're used to here on Earth, a solar storm is an interconnected set of processes. Both in space and on Earth, a developing storm can be intensified by background conditions or by merging of disturbances that don't normally encounter each other. Currently, NASA data archives house about 12 petabytes of space weather data, and this is increasing daily, and it's comprised of all kinds of different space weather observations, different instrument types, different things going from the sun all the way down to our upper atmosphere. And as I said, we know that captured in this data set is the web of processes that can produce a superstorm. But how do we detangle the information to find these signatures? So we were approached by AWS, Hannah Marlowe and her team, to partner on an AI/ML project using our space weather data set. And so we thought, what a great opportunity to actually work on superstorms. But there was one huge complication when we were going to apply traditional machine learning techniques: the rarity of superstorms. So what we did, instead of doing sort of the supervised learning, was we focused on knowledge-aided machine learning, specifically anomaly detection. So we're looking for those signatures that really don't conform to the normal expected behavior of the space environment. Extreme events in space weather are particularly amenable to anomaly detection because fair to moderate space weather makes up the vast majority of our data sets. And so it kind of provides a perfect, quiet baseline on which to identify anomalies. And the other thing is, using AI and ML, we can use every single piece of data that we have on superstorms. It kind of relies on classifying superstorms based on anomalies instead of the usual magnetic indices and various other parameters that scientists use to categorize their storms. So the other issue, there are very few historical examples that can be used to train our algorithms. The vast majority of the observations actually take place much earlier. And so what we did is we used we leveraged for space science the investment that the industry has made in developing sophisticated anomaly detection algorithms, things that you would use to identify unusual patterns maybe associated with bank fraud or web server attacks. And that's what we used to investigate superstorms. It also allowed us to look at all of the data kind of simultaneously and pick up trends either happening at the same time or even time lagged as we looked at the different areas. So one thing that was a problem for us is finding something that we absolutely knew was a common signature of a superstorm. And that was one of the most spectacular phenomena that I've ever seen occurring in nature, and that is the Great Red Aurora. These things can extend to exceptionally low magnetic latitudes and cover up to 95% of the sky. During that Carrington event in 1859, blood red skies could be seen as far equatorward as Cuba and Jamaica. People could literally read by the light of the aurora, and fire trucks were actually sent out to find and fight what were thought to be forest fires. So now we needed to identify data sets which existed at the time of reported Great Red Auroras. Unfortunately, not many were available, as most of the storms associated with these predated our very sophisticated data system that we have now. So we had to turn to operational data sets that were not originally intended for science. And here we partnered with Colorado University in Boulder to work on sort of older operational data sets and kind of clean them up, remove the nuisance signals, remove the detector anomalies, and get a scientific product that we could actually use. So one thing that we found was we did know that in order to produce a large Great Red Aurora, we need to have an awful lot of very low energy electrons, and I mean a lot of them. And this is sort of counterintuitive because this is a really big event and we're looking for low energy signatures. If you had higher energy electrons, it would actually produce the more common green aurora, but we don't see green aurora, we just see red. So, you know, again, counterintuitive. The whole energy during a big superstorm actually drops. So it was hard to actually explain that. But we found that it does recover after the storm, and that maybe was a signature of a superstorm. So after working with literally years worth of data, we found another clue. And that is that the precipitation associated with energetic ions, or positively charged particles, was actually bifurcating, and it was coming much lower in latitude than the electrons. Normally you'd see them at the same latitude. We realized that these sort of soft ions were actually kicking what would normally be a sub-visual signature of the aurora. It was actually giving it the energy and kicking it into the visible range, hence spreading the aurora and making it cover that much bigger latitude. So now we have a couple of signatures that are in common. We have the drop in energy, we have the large population of low energy electrons, and we have this bifurcation of the two populations. Now we have signatures that are peculiar to superstorms. So this led us to the production of a storm scoreboard where the extreme scores indicate superstorms. You can see the more usual one there, which is with a sort of a more typical storm, and then those beautiful red aurora with the superstorm. So the next steps for us include adding sophisticated data sets from our Heliophysics System Observatory that aggregate the observational data from more than 50 spacecraft containing now images, time series, and telemetry data spanning from the solar corona all the way through the heliosphere to our Earth's upper atmosphere. And with the aid of our sophisticated machine learning technology, we will sort of continually pre-process and combine and develop visualizations that will drive future heliophysics research and innovation. So using this very simple signature that literally was previously hidden, we can now study what other signatures may exist that will allow us to identify, understand, and eventually predict these most devastating space weather events. And it's important that we do it now. We are in a new solar cycle. The sun has an 11-year solar cycle. You're looking at data there from the last solar cycle. You can see the contrast of solar minimum to solar maximum with the sun. December 2019 marked the beginning of solar cycle 25, our current solar cycle, and the sun's activity is already ramping up and will continue to do so until we get to solar maximum that is predicted for 2025. Now, in this new solar cycle, we are already seeing much higher levels of activity than were predicted based on the last solar cycle. It will, of course, impact our lives and our technology here on Earth, as well as our astronauts in space. But more importantly, this is the first solar cycle that many new commercial and government stakeholders will actually have to navigate in orbit. We've already seen a pretty big event that happened earlier this year. It was actually a fairly small storm, a fairly mediocre storm. It arrived, it mixed with background conditions and different processes, and it actually had a dramatic heating of the whole atmosphere. It lifted up our atmosphere and meant that the newly launched Starlink spacecraft were now in an area of very intense orbital drag, and they could not reach their operational altitude, and they re-entered. And so it is very important that we work on these events, we understand what is causing them, and then we can actually predict and mitigate the biggest events. And so I'll wrap up by saying, the more we understand what causes such space weather, and the more we can improve our ability to forecast and mitigate the effects. The power and speed of AWS with the analyses to predict our superstorms can be carried out by sifting through as many as over 1,000 data sets at a single time. The knowledge process is guided by our accumulated knowledge about superstorm features and by simulations to understand those interconnections. And since our anomaly detection algorithms improve automatically with experience, we know that there's so much more potential for discovery of new anomalous features that have significance to superstorms and even to everyday space weather. So with this unsupervised learning, we are likely to discover things that we just literally did not know before. And with this partnership between NASA and AWS, we are discovering the questions that we need to ask today to drive science and innovation of tomorrow. Thank you very much.